All right, we're going to start today then with a review question from something that we saw at the end of Monday's lecture. So, question here is this. You've got a structure. Structure here is methanol. Click on the atom that has the most negative, or excuse me, the greatest electron density. So the area that would have the greatest partial negative charge. If you're not sure exactly what that means, remember, we use electronegativity to talk about the ability of an atom to draw electrons to itself. Something that has a great drawing power is going to have a more negative kind of charge than other things. So the key to this particular problem was electronegativity. And since we're looking for negative density, negative partial negative charge, we need to find the element that is the most electronegative in this compound. Question is, how do we do that? So what is the general trend in electronegativity as far as the periodic table is concerned? Yeah, so we're going from bottom left to upper right. Bottom left would be the least electronegative. Top right would be the most electronegative. And so if fluorine is my anchor point, if fluorine is the most electronegative element, I'm looking for the elements that are closest to fluorine. And so oxygen being the next door neighbor, oxygen is the second most electronegative element. That would be the element I'm interested in this circumstance. So oxygen would be the element that, because of its high electronegativity, it's going to draw those electrons to itself. And the more electrons that end up near this oxygen, the more negative that center is going to become, because, again, we're looking for an unevenness of sharing. If something's electronegative, it's going to pull those electrons in that direction, which means it's going to look more negative, and the thing that it's pulling from is going to look more positive as a result. So I'm not going to belabor the point of the homework assignment that I had you do. What we're going to do today is basically just skip to the part here where we start talking about molecule drawing. And in molecule drawing, we need to establish a few ground rules, let's say. So first and foremost, molecule drawing for molecular compounds is basically a four-step process. The first step is a step that you saw in that that video that you watched, that you went through as part of the assignment for last night. How do I determine the number of valence electrons? Well, that's relatively straightforward. I look at the periodic table. Periodic table tells me by group how many electrons I should expect for a given element. I add all of those together. That tells me the total number. Second thing, I need to determine the center atom. center atom is usually the least electronegative atom. And so here's where that electronegativity stuff really becomes important to us. It's not just in determining, is this bond polar or non-polar? It's how is this molecule constructed? Third thing I need to do, I need to draw the simplest structure. In the simplest structure, basically looking for one thing. Center atom in the middle, everything else around that center atom connected with single bonds to the center atom. And then filling out everything with pairs of electrons so that every single atom in that compound obeys the octet rule. Now, will this simple structure be correct? Sometimes yes, sometimes no. That's what step 4 tells us. Step 4 tells us that we need to compare the number of valence electrons in the Lewis structure to the number that we determined at the beginning. If they are the same, then we have what is called a valid Lewis structure, meaning it meets all of the basic criteria in terms of it's put together correctly, all of the atoms are obeying the octet rule, and it has the correct number of valence electrons. At minimum, we should always try to meet those basic requirements. If my number in the simple structure does not match the number of valence electrons, then I need to do one of two things. I need to either add more bonds if I have too many electrons, or I need to add more dots if I don't have enough. And the sub-steps in number 4 there will tell you kind of what to do in each case. Rather than go through the details of each of them, we'll address them when we come to it. So this is the primary focus that we're looking at today, is looking at these molecular compounds, drawing their structures, drawing them properly. Along the way, we're going to talk about these concepts of resonance and formal charge. A couple of things I want you to consider as we're doing so. The goal of our molecule drawing is always to draw the best Lewis structure. Now, what does the best Lewis structure look like? Well, at minimum, it has to be valid. So again, has to have the proper number of electrons. Everything needs to be obeying the octet rule at minimum. Beyond that, let's say I have a scenario where I can draw a Lewis structure multiple ways that yield valid structures as a result. How do I tell the difference between the two, or between the three, or however many? The answer to that question largely fits on the idea of formal charges. And for formal charges, we have to remember there's a formula here. Formal charge is equal to the valence electrons minus the number of bonds for that element minus the number of electron dots around that element. The best structures have the lowest formal charges wherever possible. So if it is possible to draw this particular structure that had 0 formal charge for all of the atoms involved, that would be the best structure. Now, that may not be feasible. So, for an ion, for example, it's impossible to have formal charges all equal to 0 because this last bullet point tells us the sum of the formal charges has to equal the overall charge. So if I've got a +1 ion At minimum, I'm going to have a +1 formal charge somewhere. When I have non-zero formal charges, they have to make sense. And what do I mean by that? Generally speaking, that means they need to be as small as possible. So +1, -1 as formal charges are far more common than +2s or -2s or +3s or -3s. The other key factor there is, again, tying back to electronegativity. If we have electronegative elements present in the molecule, those are the ones that need to have the more negative formal charges. So if I've got fluorine, for example, we're not going to see a +1 formal charge on a fluorine. That doesn't make sense. Fluorine draws electrons to itself. A positive formal charge states exactly the opposite, that it's pushing electrons away. So we've got to have some sense coming out of this. If I've got negative charges, they need to be on electronegative elements. If I've got positive charges, they need to be on less electronegative elements. So let's move on to talking about some actual examples here. So I'm going to ask you to pull out the handout that I gave you. We're going to go through it piece by piece here. And we're going to kind of highlight some of the key features of Lewis structures as they come up. So let's start with this first one here. In this first one, we've got a water molecule. First step, I need to determine the number of valence electrons. So I've got 1 for hydrogen because it's in group 1. And I'm going to multiply that by 2 because there are 2 hydrogens. And for oxygen, oxygen's in group 16. So 6 valence electrons for that. 1 times 2 is 2, plus 6 is 8. So the formal structure for water has to include 8 electrons. That was step 1. Step 2, I need to determine the center atom. Ordinarily, the center atom would be the least electronegative element, which would be hydrogen. Yes. 6 valence electrons because it's in either group 16 or group 6A. That column has 6 valence electrons. So based on electronegativity, we would say hydrogen is the center atom. Here's the problem. Look at where hydrogen is on the periodic table. Its energy level, the first energy level, can only hold 2 electrons. Hydrogen and helium are notable exceptions to the octet rule because their energy level only holds 2 electrons. So sometimes you'll hear hydrogen and helium referred to the duet rule instead of the octet rule. And that's just a way of kind of stating they only get 2 electrons instead of 8. Hydrogen can never be the center atom because it only can hold 2 electrons, which means it can only make 1 bond. Center atom needs to be able to connect to more than one thing. So by default, oxygen's my center atom. So I'm going to put oxygen in the middle. I'm going to draw single bonds to the 2 hydrogens on either side. And now I need to fill out octets with dots. So hydrogen 2 electrons in that bond, that's all that it needs. It needs no more. Oxygen, I've got 2 electrons here and 2 there, so 4 already hung up in bonds. To get to 8, I need 4 more. So I'm going to draw in sets of dots, and they always come in pairs. 2 sets of dots give me 4 electrons. 4 electrons in dots plus 4 electrons in bonds gives me 8 electrons overall. So I've now satisfied oxygen's octet. That was step 3, simplest structure. Step 4, evaluate. How many electrons are in this structure compared to how many I should have? So I can see I've got 2, 4, 6, 8 electrons in this structure. I'm supposed to have 8 electrons. So I'm done. That's all I needed to do. Yes. So that's what we're going for. So we're taking a look. Does the structure that we draw match what we were supposed to get? If the numbers match like they did here, then we don't need to do anything further. We have drawn something that meets the minimum criteria. Everything's got an octet that's supposed to have an octet. Number of valence electrons matches what it's supposed to be. Those are the 2 minimum criteria for a valid Lewis structure. Doesn't always mean we'll get the best Lewis structure. That's where formal charge comes in. But at minimum, you're going to get something that we can point to and say, that's valid given our rules. All right. Other questions here? All right, let's look at the second example then. Here we've got oxygen. Oxygen, group 16, 6 valence electrons, times 2, total of 12 electrons in the structure. So step 1, I've got the number of electrons that I'm supposed to. Step 2, I've got to determine the center atom. Okay, here's where we can call timeout. I've only got 2 elements in this particular molecule. So neither of them are going to be the center atom because they're really just bonded to each other. So if I have a molecule like this where there are only 2 atoms, I don't need to worry about the center atom. I'm just going to draw them as bonded to each other. So I'm going to draw these 2 oxygen atoms bonded to each other with a single bond. And now I just need to draw in the remaining electrons to fill out the octets. So 2 electrons here, 4, 6, 8 for the oxygen on the left, 2 electrons in the bond, 4, 6, 8 for the oxygen on the right. Here is my simplest structure. Single bond, everybody's got an octet. Is this the correct structure? I need to count to find out. When I count 2, 4, 6, 8, 10, 12, 14. This structure has 14. I compare it to the 12 that I need, and I go, wait a second, they don't match. Here's where I can stop myself and say, okay, hold on. This structure was good, but it's not valid. Why is it not valid? It has too many electrons in it. How do I handle that? What do I do? Well, coming back to the notes here, The notes tell us if my structure has more electrons in it than what I calculated, I need more bonds. How many more bonds do I need? Well, it depends by how much I'm over. For every 2 electrons I'm over, I need 1 more bond. So we were 2 electrons over here, so I need just 1 more bond. And in this case, since there's only one place to put it, I don't need to wrestle with myself too much to figure out where it goes. I'm going to redraw this structure because this one's no longer correct. I'm going to redraw this structure now with a double bond. And now that I have a double bond, remember, each one of these lines represents 2 electrons. So a double bond represents not 2, but 4 electrons. I need 4 more on each side. So now when I go and do my counting, 2, 4, 6, 8, 10, 12. This has 12 electrons in it, which is what it's supposed to have. This is the valid structure. So the valid structure for oxygen is one with a double bond. All right, questions with this example? All right, I want you to skip down with me to the very last one now. Let's talk about ozone, O3. In ozone, I've got oxygen, 6 valence electrons, and there are 3 oxygens, so a total of 18 electrons in the structure. Now, all 3 atoms in this case are oxygen, so oxygen is obviously going to be the center atom. So I'm going to put oxygen in the middle. I'm going to connect it with single bonds to 2 other oxygens. Filling out the octets now, I have 2 from the bond, so I need 4, 6, 8 on the left. Same thing on the right, 2 in the bond, 2, 4, 6, 8 to fill it out on the right. In the middle, I've got 2 bonds, 1 on each side, so that's 4 electrons. I need 4 more to get me to 8. So there's my simple structure. All the octets have been filled. How many electrons are we looking at? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This structure has 20 electrons in it. It's only supposed to have 18. Now we've got a problem. It's the same problem that we just saw in the previous example. But it's got a slightly different flavor to it here. I know I need to add 1 more bond. The question is, where do I add it? So if I redraw my structure, so again, we know this is wrong. If I redraw my structure with oxygen being single bonded, I know I need a double bond somewhere. Question is, does it go on the left or does it go on the right? How many of you think it goes on the left? How many of you think it goes on the right? How many of you don't know? Here's the trick of this question. It doesn't matter. It doesn't matter. Why doesn't it matter? Because the truth of the reality is, it's actually both. The truth of the reality is, it's actually neither. It's both and neither at the same time. What we are describing is a phenomenon known as resonance. So in a resonance structure, we have this very kind of dilemma that we just described, where I need to assign an additional bond, but the choice of where to assign that additional bond is arbitrary. This structure on the left is equally likely to the structure on the right. Now, why did I say that it's both present in both places and present in neither place? Well, the reality is that if I'm representing the double bond with my arm and this remote, and the single bond with just my arm, this molecule is not fixed as double bond on one side and single on the other. That extra set of electrons is moving from side to side, side to side, side to side. This is a phenomenon known as delocalization. Now, if that term sounds familiar, we used that term on Monday to describe the electrons in a metal sample. Remember the idea of the sea of electrons, those electrons belonging to all of the metal atoms at the same time and being able to move freely throughout the metal sample and give the metal the properties that it has. Delocalization can occur in covalent compounds as well in these kinds of resonance forms. And what is happening there is, again, those electrons are being passed back and forth between the two bonding areas. And so that extra bond doesn't belong to one side or the other. It's kind of a hybrid of both. And so when we talk about resonance structures, when we draw resonance structures, the picture really isn't complete unless we have both or all of them present at the same time. And that's what makes this kind of phenomenon interesting. So this is resonance. And we see resonance happen in these kinds of situations where we are assigning extra bonds and we're not exactly sure where they go. It seems like it's an arbitrary choice. And the reason it seems like it's an arbitrary choice is because it is, in fact, an arbitrary choice. And so when we find that situation, we need to make sure that we represent both sets of possibilities. Or in some cases, it might be more than two. It might be 3 or 4, depending upon what it is that is showing resonance. Right? Any questions about resonance? That's kind of a funky topic, but once you see it in action, you can see where we're coming from with it. All right, I'm going to ask you to jump up again. So leaving ozone behind, let's go back up to PF5. Because in PF5, I want to illustrate another something that's kind of funny. Let's start with the structure itself. In PF5, phosphorus pentafluoride, excuse me. We've got phosphorus, Phosphorus has 5 valence electrons because it's in group 15. And we've got fluorine. Fluorine has 7 valence electrons because it's in group 17. And there are 5 of them in total. 7 times 5 is 35. 35 plus 5 is 40. So I know that my structure is going to have 40 electrons in it. Now, between phosphorus and fluorine, this is an easy decision for the center atom. Fluorine's the most electronegative element, so the chances of it being the center atom are pretty limited. Phosphorus is going to be in the middle. So I need to show phosphorus as the center atom, and I'm going to put my fluorines around it. 1, 2, 3, oh, wait. Where's that 5th fluorine go? Okay, I could do that. Make ourselves a little fluorine train there. Will it work? All right, so let's go ahead and assign octets for everything. For these outer fluorines, we've got 1 bond. That's 2 electrons. I'm going to need 6 dots to get to 8. For this interior fluorine, I'm going to need just 4 dots because it's got 2 bonds. Let's count it up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Oh, we're 2 electrons short. Here's the other problem. Everything's got an octet. Where would we put the 2 electrons that we need to fill in anyway? There's a concept we haven't talked about yet. The concept is, when is it okay to break the octet rule? And that's an interesting question. Because it can go in 2 different ways. So first of all, it is possible to break the octet rule by not having enough electrons. We see this very commonly for group 13 substances. We see this a little bit in group 2 substances as well. So beryllium and magnesium in particular are capable of making covalently bonded substances, and they rarely follow the octet rule when they do. Same thing for boron and aluminum. Rarely do they form substances that actually adhere to the octet rule. The other circumstance, the one that we're looking at, is it okay to break the octet rule going the other way, where we have more than 8 electrons? And the answer there is yes, if. What is the if? Well, there's a couple of ifs. One, I have to have an atom capable of storing those extra electrons without going to an additional energy level. Which means I need to have available d orbitals. Where do I find those d orbitals? Starting in the 3rd period. So again, remember from our configurations discussion, That third energy level has s orbitals, has p orbitals, has d orbitals. Now, the elements in the third period aren't using those d orbitals. The d orbitals are empty, which means the possibility exists that they could be filled if the circumstances were correct. And so the second part of that, when are the circumstances correct? Usually we see this when we have bonding to highly electronegative elements and we have formal charges taking place, where formal charges end up coming closer to zero as a result of this breaking of the octet rule. So if we come back to our example here, we drew this version of PF5. It was still 2 electrons short. So we know that we need to add 2 more electrons. And our rule of thumb says if we need to add electrons, the center atom is always the place to do it. Couldn't do it to fluorine anyway. Fluorine's in group 2, or excuse me, period 2. There's no d orbitals available to it anyway. So I've got to put it here. Now, what does that do to formal charges? Well, from a phosphorus perspective, 5 valence electrons for phosphorus minus the 4 bonds that we had it made, minus the 2 dots that I just put on it, I've got a -1 formal charge for the phosphorus. For the fluorines, there are 2 different kinds. Remember, there are the exterior fluorines, where we had 7 valence electrons expected, 1 bond, and 6 dots. Their formal charges are 0. That's good. That's what we would want. What about that fluorine that has the 2 bonds, though? The 2 bonds and the 4 dots give it a +1 charge. Now we have a problem. We went through this whole thing saying highly electronegative elements should have negative charges, if anything. And yet we have the most electronegative element there is, showing a positive charge as written here. That should cause us to rethink ourselves a little bit. And the way that we can rethink ourselves is, well, wait a second. I had to break the octet rule to do that anyway. What if I broke it by making more bonds instead of more dots? So if I put that phosphorus in the middle and I throw out 5 bonds to fluorine and I fill in all of my dots, what does that look like? Well, this time, phosphorus is still 5 valence electrons, but now I have 5 bonds and no dots. No formal charge there. All of the fluorines are the same. They're all exterior fluorines now. 7 valence electrons, 1 bond, 6 dots. Its formal charges are 0 as well. So the octet rule allowed us to do 2 things. First of all, it gave us a valid structure. And second, the formal charges on that valid structure are 0. So even though we had 2 ways of doing this, drawing it out, they're not equivalent. So this is not an example of resonance. This ends up being an example of preference. This structure on the right is definitely preferred to the one on the left. And we can use formal charges to help us make that argument. Because the formal charge tells us hey, wait a second, this is a more favorable set of charges than these ones. All right, any questions with that? So this is where we can use formal charge to help us evaluate structures. This is also an example of how we can break the octet rule and why it is necessary to break the octet rule in certain circumstances. So we got through half of these. The other four, the middle four here, that is going to be the homework that you do for assignment 7-2. One note that I will give you that will help out immensely with the nitric acid. Nitric acid is what we consider a multi-centered ion or substance. And what I mean by that is when we have these acids that are polyatomic, that hydrogen doesn't attach to the center, it attaches to one of the oxygens. So the frame is going to look like this. The frame is going to look like this. What you'll need to figure out is how does the rest of it go together? And I will warn you, there is a resonance component of this one as well. There are two equivalent structures that are possible. So just something to keep in mind as you're working on that tonight. As you're finishing here, go ahead and fill out this last question so that you can get that last participation point. And on Friday, again, Friday's a bridge day. We're going to clean up the last little bits, kind of bringing in stuff that we talked about in thermochemistry and bonds. We're going to bring that along, and we're going to also start to go from two-dimensional drawings to three-dimensional drawings. We're going to say a whole lot about kind of where we go from here in terms of how we interpret it and what we can do with it. Have a great day.